Uh, but we're just going to do um, a few of the problems today, and then we'll finish up on Monday. So I think I'm going to do page 19 with you, and then page 21 to 23 is going to be what your test on Tuesday will look like. Very similar to page 7, and I think we can probably get through parts of it on Monday, and then I'll give you a morning review worksheet that you can take home to practice Monday night, and then I'll have help session over the course of these days as well. So I'm available advisements between today and Tuesday. Monday morning, 7:30 help session, afternoon help session, and Tuesday morning, just going over like these types of problems if you need additional help. All right. And so today I want to just finish up with page 19, and then we're going to start looking at an overview from all the way from the very beginning of the school year with limits and continuity. So we'll try to work through some pages, and whatever we don't finish, I'll check on Monday. So your homework over the weekend is to study for the test, but then also I want to check pages 1 through 4 in packet 2. Okay, so page 19. So sometimes a derivative graph is given to you, but the definition around that derivative graph is a little bit different. So I want to highlight those distinctions so we know how to approach these problems depending on how the derivative graph is presented to you. So here's the first variation. The figure shows the graph of f prime, so it tells you outright this is an f prime graph. The areas of the region are given. So if it was a geometric shape, then you will be expected to find the area if it was like a triangle or a semicircle. But in this case, the areas are given to you because these are not nice geometric shapes. So let me highlight these shaded regions here. So we're talking about this region, this region, this region there. Okay. So they tell us that the areas are 7 from area of 7 from interval from -3 to -2. So that's positive, right? Since it's above the x-axis. And then from -2 to -1, sorry, -2 to 1, the area of 6, but it's below the x-axis, so we say what? -6. And then between 1 and 4, area is 8, but the region is below the x-axis, so we'll be what? -8. Okay, so they say that given that f of -2 equals 4, find f of -3. So if I want to find a point on the f of x graph, and I only have the areas to work with, but I have a starting point, then I can use this formula here. Okay, and this is we gotta know this one here. This is basically first theorem, but it's rearranged so that f of b equals f of a. So basically, any position I'm looking for, it's going to be my initial plus displacement. Okay, I'll show you 2 different ways to do this if you don't want to memorize this formula. Okay, so let's start off with this. I'm looking for f of -3. but I'm given f of -2. So I'm going to say, okay, I'm looking for f of -3. So f of -3 equals f of a. So that's the given, that's the initial. So that's f of -2 plus however much accumulation that I've gotten between these two endpoints. So the integral from -3 to -2 of f prime. Okay, so f of -2 is what? 4. So this is my starting point, this is my ending point, and then this is how much progress I want to make. I want to figure out how much progress does this object make between the starting point and ending point. So -3 to -2, what is that going to be? What's the area under the f prime graph? 7, yeah. Oh, sorry. What did I do here? Yeah, my bad, my bad. Hold on. Sorry, guys. So because I am starting at -2, these have to be in agreement. My lower bound is going to be where I start, and my upper bound is going to be where I end up. I'm starting at -2, and because that's what I'm starting with, right? I'm starting at -2, and I'm ending at -3. However, these are backwards, right? This is going backwards. This is going from right to left. So what can I do to make it so that I can go from left to right? I can flip the bounds and change the sign, right? Okay, so now we can go to our graph. What is this portion equal to? That's 7. And then the negative is going to carry over. So then 4 minus 7 is 3. Okay, let me show you another way to do this if you don't want to go through this formula. Okay, so you know that you're involving the area or region between -3 and -2. So you can just go ahead and I'm going to put that work over here. So let's say you already know it's involving -3 and -2. So you're just going to go from left to right to begin with. And you're just going to set it up this way. Okay. Now, first theorem. Okay. What will first theorem look like? F prime becomes what? Yeah, and then I plug in what?
2 minus.
Yeah. Okay. So if I do it this way, there's no need to memorize this formula because you're just using first theorem. Now, now we're just going to fill in what we know and then find the missing information. Okay, so what's the integral from -3 to -2? 7 equals, what's f of -2? 4 minus f of -3. Okay, so we're just solving a simple equation here. If I want to solve for f of -3, I'll move that f of -3 to the left side. Make it positive, subtract 7 to the right side. 4 minus 7 is -3. Because the integral from -3 to -2 is from left to right. It's above the x-axis, so it's positive 7. So if you want to do final equals initial plus displacement, that's fine. But if you just feel like, okay, I'm just going to use first theorem and just spell it out and then fill in the values I know and solve for the missing variable, you can work it that way as well. Okay, let's try f of 4. So I'll go through both ways. If I want to find f of 4, my final is initial plus displacement. So I'm starting at -2 and I'm ending at 4. So f of -2, I know that, that's 4. The area from -2 to 4 is what? What is that going to give me? What does that add it together? -14. 4 minus 14 is negative. Okay, so if we want to work it out this way, where we just start off with this, we can say, okay, I know I'm basically involving the area from -2 to 4. And if I spell this out using first theorem, I can say, well, I know this is equal to f of 4 minus f of -2. I know this region is -14. I know f of 4 is -10. And I just rearrange it and solve for f of -2. -10 plus 14 is 4. Oops, sorry. 4. My bad. F of 4 is not negative. F of 4 is, I got these mixed up, sorry. F of -2 is 4. So I have that information. I don't have this information. Okay. So add 4 to both sides. F of 4 equals -9. Okay. The second variation is where they give you a definition for accumulating the graph. If that's the case, there's no need to do final equals initial plus displacement. You should use this formula. This is what we've been doing with our recent problems. Okay, so for instance, let's say I want to do g of -3. Okay, again, same thing, right? Same. This is still 7. This is still -6. This is still -8. Okay, so if I want to this feels a little bit easier because I can just plug into the formula. Whatever this gives me, I'm just going to accumulate that area. There's no need to worry about any additional pieces. So if I want to find g of -3, I just put into the formula where the -3 is supposed to go. And I'm just going to read the graph. Okay. Now, once this is in, I see that my bounds are out of place. So I am going to pull a negative out and swap the signs. So the integral from -3 to 1 is what? What is the accumulation of these two added together? Seven minus 6 is equal to what? 1 with a negative in front, so I get a -1. To find g of 4, I can use this definition here. So 1 to 4 is below the x-axis. That's -8. There's no need for me to adjust the bounds. I'm already showing from left to right. So -8 below the x-axis. Okay, so this is a little bit easier. There's no need to worry about a difference outside information. But if you're given where you're just given a starting point, then you do need to use first theorem to kind of fill in the missing piece and find what you need. Okay, so let's start looking at today's packet. Okay, so and then you get thanks.
I did 19 earlier too. So
Got it.
Whenever.
Thank you. All right, so back all the way to limits. Okay, so let's review some of these. Oh, and by the way, the key is attached. The key is attached in the back of your packet. So what does the limit tell us? The limit tells us the y value that the function is approaching. That's the key thing from both sides. Okay. If the graph, basically if there's a hole in the graph and you see the graph is connecting to the hole from both sides, same hole from both sides, the limit is going to exist. So a limit is the value that a function approaches from both sides as that function's x value gets closer and closer to some number. Yeah, it's next to the tissue box there. Yeah. So if you want to find a limit as x approaches -3, I basically have to figure out, is the graph approaching the same y value from both sides of -3? So I think the best way to do this graphically is force yourself to pick points on both sides of -3 on the graph. So I'm going to pick points on both sides of -3 on the graph. I'm going to highlight those points. And now I'm going to draw an arrow towards -3 along the curve. And now I'm going to ask myself, are those two arrows pointing to the same y value? Yes, right. They're both pointing me towards a y value of what? 2. So because there's an agreement with the two arrows, we can say that the limit exists and the limit is 2. Even though the point is over here, you may be tempted to say, oh, the limit is going to be at 1, but it's where the graph is headed, not where that island point is sitting. All right, number 2, f of -3. F of -3 is just asking for the point. So where's the point defined at -3? 1. Yeah, so we see there's a hole there. The limit exists towards that hole, but the point exists at 1. So that's the big distinction between limits and ordered pair. Now, if the graph is connected, then your limits and ordered pair will be one and the same. But as soon as you have a hole, as soon as there's a break involved, then that's where you're going to begin to distinguish between limits and ordered pair. They're not going to come out the same. Okay. Number 3, limit as x approaches 3 from the left side of 3. So this is a one-sided limit. This is basically saying pick a point on the left side of -3 and then just follow that arrow. Okay, where is that arrow headed? So if we're approaching, so if I pick a point to the left side of -3, that's this point. And if I'm headed towards -3, the arrow is going to point to the right. And where is this arrow headed? Y value of what? 2. And if I pick a point on the right side of -3, and if I head towards -3, this arrow is also pointing towards what? 2. So here's the big distinction is that if your one-sided limits are in agreement with each other, then your true limit will also exist. But if your one-sided limits are not in agreement, if one is headed towards 4 and the other headed towards 5, and there is a disconnect between the arrows, then there is no limit. The limit does not exist. Okay, let's see if we can continue and get some more practice here. All right, limit as x approaches 0. So this is asking for the full limit here. So I'm going to pick points on either side of 0. I'm going to draw an arrow towards 0. Is this arrow headed to the same y value as this arrow? No. So therefore, the limit does not exist. Okay. F of 0 is only asking for the point, so f of 0 is equal to what? 2, because the point is defined here, right? The whole is not defining any point there, so it's 2. Limit as x approaches 0 from the left side of 0, that means I'm just basically following this arrow here. I'm picking a point to the left side of 0, and I'm headed towards 0. Where is this arrow headed?
Point.
Yeah, it's going to be some decimal value. Even though it's a whole, we can still do one side limit. It's still heading towards a value. So we can say 0.8 or 0.9, but our best, we can only do an approximation since we don't know exactly what that y value is. So any approximation is fine. If I pick a point on the other side of 0, I'm just looking at the arrow from one side here. Where is this arrow headed? 2. And so this is the reason why the limit as x approaches 0 does not exist, because one side and the other side, the arrows are not headed towards the same destination. Okay, limit as x approaches 2. So I'm going to pick points on either side of 2. I'm going to draw an arrow towards 2. Are the arrows headed towards the same y value? They're both headed towards a y value of what? F of 2 is equal to 1. Approaching 2 from the left side of 2, 1. Approaching 2 from the right side of 2, 1. So here's something that I want to show. I want to identify for us. If everything is in agreement, your order pair, your one-sided limits, and your full limit, if they're all in agreement with each other, that means there are no breaks in the graph. Okay? There are no holes, there are no asymptotes. It's just going to be a nice connected graph. But as soon as you see differences between those data, then it's because there's some sort of a break occurring, either a hole or an asymptote. Okay, evaluating limits algebraically. Let's look at some of that. So if we see a limit problem, no matter what the problem looks like, as long as we're approaching a real number, the first thing we always do is what? Yeah, let's just test that value, right? Let's see what's going on. We don't know what's, without testing it, we don't know what's going on. Is there a hole? Is there an asymptote? Is it connected? So first thing we should always do is just plug in that x value. Okay, so in this case, what are we gonna do here for number 1 first? Plug in the 3. Yeah. Don't worry about the one-side limit. Sometimes that one-side limit is a distractor. Sometimes doesn't even mean anything. So plug in 3 and let's just see what happens. Okay, so if I plug 3 in for x, numerator I get
Here.
0. Denominator, I get what do I get in the denominator? 0 as well. 9 minus 6 is 3. 3 minus 3 is 0. So what does this tell us? Indeterminate. Yeah. So does the limit exist? Well, we do know, we just haven't found it yet. Right. So this basically says that there's a hole in the graph, right? That algebraically it's not giving us a number that's going to be helpful, but it's a hint. It's a hint that there's a hole, the limit exists. We just have to do more work to get to it. So we can factor and reduce and reevaluate, but now that we have L'Hopital's rule available to us, I think most of us will just prefer to do L'Hopital's rule. So L'Hopital's rule just says, take the derivative of the numerator and denominator and then reevaluate again. So what's the derivative of x minus 3? 1. What's the denominator of x squared minus 2x minus 3? Reevaluate. Plug in what? What do we get? Two x minus 2. What do you get in the denominator? 4. 1 over 4, yeah. So that's our limit. And if we're asking about, wait, what about decimals, right? Don't we have to do decimals with VC one-side limit? That's only for certain scenarios, okay? If we can get to our real number without having to deal with that one-side limit, then that's just a distractor. Okay? It's not going to mean anything. Okay. When it does mean something is if there's an issue, if there's like a real issue, like a vertical asymptote. Okay, then we can look at it more closely. Okay, so let's look at number 2 here. First things first. Like in 3. Negative 3. Okay. So negative 3 goes in for x. Numerator, I get -5. Denominator, I get. Okay. Now, what is that telling us? There's something happening here. Well, yeah, it's good. It's undefined. Yep. But how does the graph look? What's happening there? There's a vertical asymptote there. So if you think about the vertical asymptote, right, how can a graph look at a vertical asymptote? So let's look at some options there. Right, the graph could either be headed up towards what? Infinity, or it could be going down towards negative. Right, or just any variation, right? Maybe both arrows are headed in the same direction. Maybe they're both headed in opposite directions, or they're both going down. But this is just one instance, right? So we know that the limit doesn't exist, but now we look at this problem more closely. Is it even asking for the full limit? It's only asking for how is the graph approaching from the left side of -3. So what are the two options that the graph can do if it's approaching -3 from the left side? It could either go up or it could go down, right? So if we're trying to decide which one of those options towards a vertical asymptote, now we can look at what to help us do it without a calculator. Now we can look at decimals. All right, so decimals will help us narrow down the option between, because we don't know which direction the arrow is headed, and that's what decimals are doing. It's helping us to decide between those two options. Right. So what's a decimal value that is close to -3 on the left side of -3? Yeah. Right. And we're doing this without a calculator here. So 2 times -3.1 plus 1 over -3.1 plus 3. Okay. All right, we don't need a calculator because all we care about is it's going to give us positive or negative. So 2 times -3.1, that's around -6-ish, right? So -6 plus 1, is that positive or negative? Negative. How about -3.1 plus 3? Also negative. So two negatives over each other, I still get positive. So therefore, my arrow is headed up. Okay, number 3. What's different about number 3? Yeah, so we have a different set of rules for infinity. We don't plug in for infinity, we compare degrees. So if we're approaching infinity, we compare degrees. If the numerator is less than the denominator, then limit is 0. If the numerator and denominator have the same degrees, then we should look at the ratio of the coefficients. If the numerator is greater than the denominator, then it's either positive or negative infinity. Then we'll test either 100 or -100 to decide whether we get a positive or negative. Okay, so we compare degrees here. So what's the highest degree that you see in the numerator? What's the highest degree you see in the denominator? So degrees are the same. So what's my limit going to be? -1. We just look at the number attached in front of those variables. So 1 is in front of x squared, -5 is in front of the denominator x squared. So 1 over -5 or -1/5. Okay, number 4. Limit as x approaches 0. What's the first thing we do? Plug in 0, right? Okay, so sine of 0. What's sine of 0? 0. Natural log of e to the 0 minus 1. E to the 0 is just 1. 2 times 1 is 2. 2 minus 1 is 1. What's the natural log of 1? 0. So I get 0 over 0. What does that tell us?
Limit.
The limit exists. There's a hole in determinate form. What can we do to resolve this? L'Hopital's rule. Yeah. So L'Hopital's rule, we take the derivative of numerator and denominator. So here's some reminders here. Sine's derivative is cosine. Natural log's derivative is u prime over u. And e to the u's derivative is e to the u times u prime. So we'll take the derivative of the numerator and denominator separately here. So sine becomes cosine. Natural log of u is u prime over u. So what's the derivative of 2e to the x minus 1? Because that will just go in that space there. 2e to the x all over 2e to the x minus 1. So there's my u prime over u. This is now a derivative version that I can use to evaluate limit. So what's my next step? Replace every x with what? 0. And hopefully that will get us to a real number now. So this is 2 over 2 minus 1 is 1. So 2 over 1 is 2. So 1 over 2 is 1/2. Okay, another important concept from Unit 1 is continuity. Page 2.
These aren't on the quiz on Tuesday,
No,
right?
no. Okay, so continuity conditions, how can we show that a function is continuous? So there's a couple of things that we want to establish. Let me highlight those things here. First thing is, does the point exists? So we show that the point is going to exist. The second condition is, does the limit exist? So in other words, is the graph going to approach the same y value from both sides? So if the graph looked like this, it would pass the second condition, because if I pick points on both sides of the hole, both arrows are headed towards the same y value, so the limit does exist. Right. So the one side limits are in agreement. Left side's arrow is the same as the right side's arrow. And the third condition, does the limit exist where the point exists? So in this case, are these in agreement? They're not. So this one would fail. But if the point was living where the hole was, then it would pass all three conditions. All right, so let's look at number one and see if we can prove whether all three conditions can pass. If it passes, then it's continuous. If it doesn't pass all three, then there's different names that we can give these discontinuities. So number one, it says the function is defined by f of x equals root 25 minus x squared. Let g be the function defined by g of x. And g of x is this function between -5 and -3, and then it's a different function between -3 and 5. Is the graph continuous at -3? Use the definition of continuity to explain your answer. So first things first, we want to see, does the point exist? So the c value is -3. So can we find f of -3? I'm sorry, can we find g of -3? And the piecewise function tells us which one to use. If I want to choose -3, where's -3 defined? Within the first piecewise or for the second piecewise? First one, because you see the line underneath, right? So I'm going to plug -3 in for x. So -3 goes in for x. 25 minus -3 squared, that's 25 minus 9. 25 minus 9 is what? Which is? Okay, so the first condition passes. We can continue moving forward. Okay. Does the limit exist at x approaches -3? Okay. The problem is that -3 is split between two different functions. So I got to do a limit from one side and limit on the other side and see if they're actually going to head towards the same y value. So I'm going to set up two limit statements. One is approaching -3 from the left side of -3. And then the other one is going to be the limit as x approaches -3 from the right side of -3 for the second piecewise. Okay, so I don't have the graph in front of me, so I'm just using these numbers to help me see, are they going to be in agreement? Okay, so we found this already, right? -3 in for x. This is going to give us 4. -3 in for x here. What do we get? Also 4. -3 plus 7 is 4. Okay, are these in agreement? Yes, that means on the graph, the two arrows are headed towards the same y value. So we can conclude that the limit as x approaches -3 of g of x does equal to 4, because our two different graphs are consistently taking us towards the same y value. So that's the second condition. Now the third condition is easy, because you just look at what you've gathered and see, is my data the same? Is the point and the limit one and the same? Yes. So therefore, I can say that my function is what? Continuous. Okay. But we do want to, instead of saying 4 equals 4, we want to be able to write it out in this form. So we want to say the limit as x approaches 3 of g of x is equal to -3. It's equal to g of -3. Okay, one last one here, number 2. If the function f is continuous and the function is x squared minus 4 over x plus 2, and x does not equal to negative 2, then find f of negative 2. So anytime you see the word continuous, I think it's just easiest to just go through the continuity conditions and just use that as a framework or as a way of kind of helping us step through the problem. So we're trying to look for f of negative 2. And we don't know what it is. So it's okay. The first condition is unknown, but we're just gathering information. Eventually, we're going to be able to figure it out. Okay, second condition is what? Find the what?
Size of the line.
But well, essentially, it's find the limit. Now, we don't have to find both sides of the limit if there's only one function. But if there are 2 functions, then we want to take that additional step. So just find the limit. Okay. So how can I find the limit? First thing, what? What do we get? 0 over 0. So I can factor, reduce, or if you want to do L'Hopital's rule, I think that's what we'd probably prefer. Okay, what's the derivative? Denominator is, yeah. Reevaluate, we get. Oh, sorry, approaching negative 2, my bad. Yes, negative 4, right? Correct. So I want it to be continuous. So if I want it to be continuous, what needs to happen? Yeah, it's got to be, right? In order for this to be continuous, I have to be in agreement. And if I'm forcing agreement, that means this must be negative 4 because they're telling us continuous. Okay, so your homework is to finish pages 1 through 4. The key is attached. I'll send out a reminder this weekend. Okay, all right, come get your phones. Thank you.